Okay, can I start? Hello, I cannot start if you all continue to keep talking. Okay, we stopped here yesterday, right? Yes or no? Time finish, temperature finish, length, mass done, volume, I show you how to do the conversion, yes? Okay, you might need to have more practice with the volume one, but I think it's very similar to what you do in math, right? So this one, please make sure you know how to do the conversion. Okay, I want to focus on this portion. Okay, unfortunately, I didn't manage to, okay, maybe next lesson, what I'll do is I'll bring in the apparatus, then I hope you all can handle them very, okay, maybe, I don't know if I want to pass around. I'll bring the actual apparatus to the classroom to show you, okay? Because in lower sec, you didn't learn many apparatus, right? So just to recap, which one you all know? This one, right? I mean, measuring cylinder, right? In lower sec, you learn volumetric flask? No. Yes or no? No. Okay. Pipette burette, I think also not emphasized. Okay. So the only one familiar here, I guess, is the beaker and measuring cylinder. Okay. So notice that all of these apparatus here, right? They all are used to measure volume. But why are there so many apparatus used to do the same thing? Okay, because or at least in chemistry, when you go to the lab, you need to make certain choices based on what are you trying to do. So it really depends on the context. Okay, yes, we are trying to measure volume or store or volume of liquid. Okay, but there's different considerations. So in this case, what are we looking at? We are looking mainly about accuracy. Okay, because it depends on how accurate you want to be. So for example, if I just need an approximate amount of volume, estimate only. There's no need for me to be so accurate as to like take a measuring cylinder, okay, fill it up with a liquid, then I'm going to measure, right? How do you measure the liquid level in a measuring cylinder? What? Okay, by measuring it, what do you need to take note of? Measuring cylinder. There's something there, right? There's a curve shape, right? What's that called? There's a curve in the, when you measure in the measuring cylinder, correct? The liquid will be like that. What is this thing called? When, okay, you need to measure off the meniscus, right? Which is the bottom portion. I hope you can remember this. Set 1, you learn already. Okay? There's a curve on the water. So you must measure eye level to the bottom of the meniscus, right? The bottom. So how do you do it? Let's say I were to hold a measuring cylinder in front of me like that. How do you measure? Or you put the measuring cylinder on the table like that. How do you measure the volume accurately? What must you do? I can measure like that. Okay, what must you do? If the measuring cylinder is here, okay, now here, I want to measure volume, what do I do? Eye level. Eye level, so you put down. Okay, measure at eye level. What is the why must you measure eye level? What's the consequence if you don't measure eye level? Okay, you get parallax error, which is you either the volume is too high or too low, depending on whether you read from too low or too high. So you must take this into account, especially when we go to the lab. Actually, we are either going to the lab next week or week 3. So I just let you know first. Okay, so all these things you must remember because it's a practical skill. We may not test it on the test or whatever, but you must know for an exam. Because accuracy is very important. If let's say you read the wrong value, you will record the wrong value, then end up your calculation, everything will follow. Okay, so must remember the reading of the meniscus. Okay, so in what cases do I want to choose between all these? Okay, so first thing first, what is a pipette? Okay, I don't know if it's clear enough. You can see from here, right? Have you seen this in a lab? Never use, right? You like to use in lower set? No. Okay, never mind. When we go to the lab, I will make sure I will get all of you to, let you all see, okay? So this pipette is basically, it looks like that. Okay, it's basically made of glass. Okay, notice here there's a part that is protruding out. Okay, there is a mark here at the tip. This mark is for you to fill a volume up all the way. Sorry, there's a mark here. I don't know if you can see. If not, you zoom in your own picture. There's a blue color label here, one mark, and there's a brown color ring here. Okay, you zoom in your book or what if you cannot see clearly. How it works is that this pipette is designed to measure a specific volume of water, of liquid. Okay, 25 can be 20, can be 50. It depends on the size of the pipette you purchase. Okay, however, notice it's always a very nice number, like 25, right? 25.0. Or maybe it's 20.0 or 50.0. It's a very, very nice round number. Okay, so if you want to measure such a volume that is so exact like 50.0, then you will consider using a pipette. Okay, so what are the benefits or what are the advantages of using a pipette? Okay, it's very accurate because once how it works is you're gonna fill up the liquid to the ring, the brown color ring. When it reaches that ring, you stop. Then by then you already know this pipette contains exactly 50.0 cm3 or ml of liquid. Then all you have to do is now transfer and you have an exact volume of 50.0. Okay, but take note for pipette, same problem, you will have the meniscus. So when you measure the volume of the pipette, right, you need to make sure that the ring, right, there will be a brown color ring. So the brown color ring is around here. You make sure the meniscus, right, is above or is at the brown color ring. It's a brown, I don't have brown marker, so just imagine it's brown. So the brown ring at the around the pipette, okay, at this portion here, okay, this portion, okay. So once you fill that up, you transfer exact 50.0. So it's very quick, very convenient. When you get to practice, you will realize why. Okay, because I don't need to think so much. All I do is I fill up to this ring. I know I have the exact volume. Okay, whether it's 20.0, whether it's 22 point, whether it's 25.0, whether it's 50.0, it depends on the pipette itself. Yes, okay, good point. Yeah, so of course, if you look at this and then you are thinking, how do I use this thing? I just plug it in the water, in the liquid, and then it will magically the water will be sucked up, no, right? Okay, so there's this thing, you need another part called the pipette filler. Okay, so it's red in color. You will attach the pipette filler over this part. That's why there's a blue color ring here. You will attach it in. Okay, then the pipette filler, there's a few buttons for you to press. Okay, to either draw up the water or you can release the liquid. Okay, I will show you how to use it in the lab itself. Okay, very difficult to tell from the picture. Okay, so you just KIV first this. Okay, any question for pipette? Okay, I need to make sure you understand because this is new. Okay, next is the volumetric flask. Okay, so volumetric flask is this one here. Okay, so very similar in terms of the design. It's just that okay, now that it can stand by itself, right? And the volumes that the volumetric flask can hold, right, is typically larger. Maybe 100. This one is 100 mils, right? It can be 250 or possibly more. Okay, so in terms of the volume, amount of volume it can accommodate, right? Volumetric flask bigger tend to be larger volume. Okay, smaller volume more so your pipette. Okay, and maybe usually your pipette. Okay, so for volumetric flask, right, you cannot really see clearly, right? There's also a line here, very similar to the pipette line, right? One ring that surrounds it. Same thing. Volumetric flask is designed for you to top up liquid or contain liquid to an accurate amount. So in this case, it's 100 ml. When I fill my liquid up to that line, it tells me that there's 100 ml of liquid, exactly 100 ml of liquid inside. Okay. However, it's different in a sense that it's more for diluting a mixture. Okay, so what does it mean to dilute? What is diluting? Because from oral set. Reduce is dilute. Okay, yes. Okay, so reducing the concentration. So what is concentration? In your own words, what's concentration? In amount of substance in one area. Okay, in one volume of usually your volumetric flux is used when you want to dilute something. For example, if I take my solution is too concentrated, or even at home, you feel like you drink Milo, right? You feel my Milo is too concentrated, right? It's too sweet. Then what do? You add water, right? To dilute the concentration of the Milo to make it less sweet, right? So same thing here. If I find that I have a concentration of a solution that is way too concentrated, then what I will do, I will transfer my solution into a volumetric flux. Okay, but obviously it cannot be more than the volume itself, lah. So you choose a volumetric flux that can hold all your solution. Okay, transfer the solution into the volumetric flux. Okay, ideally it shouldn't be anywhere near the top. Okay, then what you do after that, you will top up with water, pure water, distilled water. Take the distilled water, transfer it, top up to the mug. Okay, after that you have a cap. You cap off the volumetric flux. Then you now need to mix it. Okay, when you mix it, after complete mixing, the solution is now diluted. Your concentration decrease. Okay, so this is how you prepare solutions of chemicals that are more diluted. Okay, so this one not very common, I'll say, but we'll get to see it. So basically, in general, for your science, right, when you want to prepare what we call a homogeneous mixture, you all know the word homogeneous? What's homogeneous? What does homogeneous mean? Is the concentration uniform throughout or not? No? Yes. Okay. Homogeneous means concentration uniform throughout. Heterogeneous is the opposite one. Okay. So if you want to make it homogeneous, you need to mix well. So for this one, right, the mixing, right, is I just tap it, then I'll just start shaking it a bit. Okay, and it's not the pao cha shake lah, you know, it's like you really have to shake. Okay, so this one, I'll bring to class, then I show. Okay, so volumetric flux, fixed volume, same as pipette, but larger volume. Okay, and the function wise usually more for diluting mixture. Okay, next is measuring cylinder. I think it's new. I mean, it's not new to you, right? So measuring cylinder, take note. Why do we? In what cases do we use it? We want to measure a range of volume. So take note, range of volume is opposite to fixed volume. Means what? I want to measure a specific some range of value lah. So for example, measuring cylinder usually is 50 cm cube. So I can measure volume from 0 all the way up to 50 cm cube. Okay. Not only that, it's also accurate to the nearest 0.5 cm cube. Okay. So it's usually we don't say dp here lah, because if I say nearest 1 dp, then you will start to round off to nearest 1 dp. It's not nearest 1 dp. Is nearest 0.5 cm cube. So what do I mean by nearest 0.5? If let's say my measuring cylinder, right? Okay, my volume of water is like that. Okay, let's say 24, okay, 25 here, 24. Okay, my volume of water is here. Then what is the reading? If it's nearest 0.5, 24.5, right? Can see? Because it's nearest 0.5. Okay? If my volume is here, what do I read? What's the value? 24.5 or 24? Okay, 24, because it's not very straight. Okay? If it's nearer to the number, you take that number. If it's in between, if it's nearer to the middle, then you take the middle number, which is 0.5, right? So imagine there's it won't be on the measuring cylinder, but you have to imagine there's a middle point. Okay, so that's what they meant by nearest 0.5. Okay, so you will not get volumes like 24.6, 24.9, impossible. Okay, unless even if your eye is super good, right, you just follow this way. Okay, so in the middle or close to the middle is the midway mark, the nearest 0.5. If not, it's the whole number only. Okay, clear so far? And okay, so why? Because the burette one, notice Okay, burette, they say nearer 0.05. So is it more accurate or less accurate than measuring cylinder? It's more accurate. In fact, it's one more decimal place. Okay, so for burette wise, take note. Okay, burette, how it looks like first is this one. Okay. Do you all see this in the lab? Yeah, the very long one. Okay, but good news is our school don't use. Okay, so some schools, right, they don't have they never purchase new one. So the old one, right, they have a rubber tube. Then what the students have to do is they always have to use paper clip to clip. If not, the water will just continuously leak out. Okay, but for our school, we are fortunate enough, we have the one with the tap. So you just need to open, close the tap to adjust the volume. Okay, so it will look slightly different from this one. Okay, which I will show you lah. Don't worry, everything I'll bring to class next week. Okay, so the burette, right, is longer in a sense that usually the volume is 50 cm cube. Okay, so it can hold to 50 cm cube, and it's really just a like long cylindrical it's just very long and cylindrical in shape lah. Okay, so what is important to take note of your burette? Same thing, it's a range of volume. It's not meant for specific volume. So no matter what your volume is, as long as it's between 0 and the maximum the burette can hold, you can always measure the volume. Okay. So example, why they say nearest 0.05 is the same thing, except now we go 1 dp higher, or sorry, 1 extra decimal place. So if your burette reading, okay, let's say this is, okay, I use similar value, 24.00. Then here I have 24.10. Same thing. When I say nearer 0. Yes. Okay, good. For what SOC? Okay. If I say nearer 0.05, what it means is similar concept here. If I'm in the middle of 24.1, okay, 1 dp, 24.0, also 1 dp, I can read off to the nearest 0.05, which is, what's the value here? 24.05. And that's what they meant by nearest 0.05. Okay, the 0.05 is here. Okay, so if it's at that mark or is nearer to the middle mark, you go to the 0.05. If it's not, same thing. If it's here, I will read 24.1 because it's closest to 24.1. Okay. If it's here, I read 24.0. Same thing. Okay. Okay, sorry, you should have 2 dp. Okay, I need to emphasize now. Okay, for burette reading, can you write down somewhere? Are you able to annotate on the ebook? Can, right? Can you write down? Burette reading must be 2 dp. Need to emphasize because when we go to the lab next week or week 3, we will be recorded. Okay, when you use the burette, you need to measure 2 dp. Okay, that means even if the answer you measure right 31 cm cube, you will be marked wrong. Even though it's exactly 31, you must put 31.2 dp. 0, 0. Okay? I mean, it's like math, right? Or your lower sec science, I think you also emphasize on exact. Even if your answer is exact, please write the decimal place. Okay, not the accuracy. Okay? So, burette 2 decimal place, nearer 0.05. It's not 2 dp, then I round off, I get like 0.079. Okay, it's either 0.0, that means it will end with what numbers? Either a 5 or 0. Okay, last number 5 or 0. 5 or 0. Okay, because we always go by the in between number, the middle number. Okay, any questions so far? Okay, maybe when I show you, then you have more questions now. Okay, because a bit hard to visualize, I think here. Okay, so the meniscus, I think I already mentioned. Just take note, right? Meniscus got 2 kinds. Okay, this one I don't really think you will get to see. So you have the concave meniscus as well as the convex one. The more common one you will encounter is the concave meniscus. Okay, so remember you must always read at the bottom of the meniscus. You imagine a straight line. Okay. passing through the bottom of the meniscus and you read off that value. When you read off that value, same thing, you must take note of the accuracy as well as the rounding. Okay, like whatever I mentioned just now, whether it's nearest 0.05 or nearest 0.5, you take note as you read. Okay, so in this case, this example, they know that this is 16, this is 17, every line is 1, right? 0.1. So it's 16.1, 2, 3, 4, 5, all the way. This meniscus is, I draw a straight line across and I notice that it's 16.40. Why they write 0.40 instead of 0.4? Because this is from a burette, so they read like that. Okay, that's my guess. Okay. So if you don't read from the off the meniscus, this is what happens. You read either too high, from too low or too high, you get a parallax error. Your number either becomes lower than higher than expected or lower than expected. Okay, so this gives rise to inaccuracy because you did not read off the meniscus properly. Okay, so just take note for this. Okay, I think this is the last one on the physical quantity. Okay, volume. Just now we're talking about volume is specifically for only liquids. Right, just now your burette, pipette, metric cylinder, you cannot store gas in there. The gas will just escape. Okay, if I want to measure or collect a gas, what do? I use this thing called the, is that right? Okay, I think textbook have it's called gas syringe. Okay, so take note, you must write gas syringe. Don't just write syringe because syringe is a very, we don't know what syringe you're talking about. Is it the doctor one? Okay, so write gas syringe. Okay, how does the gas syringe work? It's basically the same as your normal syringe, except you have this tube that connects from your whatever storage apparatus you want to use. You want to use a beaker. Okay, beaker usually not. More of your, in this case, your conical flask connected to the gas syringe. So whatever gas is produced inside by this reaction is slowly being transferred into the gas syringe. Then as the gas is being produced, right, the gas will just push against the plunger. Then you can read off the value accordingly, right? So this one is about 24 point, about 24, I'm guessing 24 cm cube. Okay, you just read off like that. Okay, so take note. What do you think? What, anyone knows what this is called? Okay, stopper. We just call it stopper, or sometimes you'll hear words like rubber band. Okay, or stopper. Okay, so what is this used for? Why do I need this? Okay, because yes, exactly. Because I'm trying to collect a gas. I must prevent my gas from escaping. Okay, if I don't do that, then all my gas will just escape. I'm not collecting anything. This thing won't even move if the stopper was not there. Okay, so take note, especially when you deal with gases, you need to make sure the gases do not escape. Okay. Okay, any questions so far for the apparatus side? Okay, please, I encourage you, please ask questions. If not, later I come back the TP or what, then suddenly, why everybody don't understand? Because every time I ask, when a teacher asks if you have question, right, it's really it's not to shame you or anything. It's really you want to address any concerns you might have. Okay, because we've been teaching for many years, right? To us, it's like if we say, then you should not understand. So please help us. Please voice out if you don't understand. If you say or what, then you ask me afterwards. Okay. Okay. Metric system. Okay, I think today we have some time. I think I'll just play this video. Okay, but the volume, the sound doesn't work though. Okay, wait. Let me try. It doesn't work, right? How do any other teachers play video? Can okay, I think, I tell you what. You have the slides, right? You can watch the video if you're interested. Okay, so basically they're talking about, I believe they might have used the example that I mentioned in class before, the one about the space shuttle. Okay, So just a recap of whatever we have covered so far. Why do we need SI units? Because we need a common standard. Okay, across all the countries, across the entire globe, we need to come to a consensus as to which unit do we want to use when we present data. Okay, and especially at international conferences. Okay, if I come to a Singaporean or I come to you and say the temperature is very hot, it's like 300 degrees Fahrenheit. Then you also don't know what I'm talking about, right? Because we don't use that unit. Okay, therefore we come together as a collective. Okay, all the scientists, we just establish. Okay, I'm gonna select A, B, C, D. These are what we call the SI unit. If I want to present my data or if I want to communicate with another scientist from another country, I will first convert to this specific unit. Okay, so the units are like your mass. Okay, come, you all help me recap. Mass, SI unit. kg. Okay, temperature. Kelvin. Length. Meter. Volume. Meter cube. What else am I missing? Time. Second. Okay, good. I think you all still can remember from lower sec. I think that's it. Okay, these are the main ones. Okay. Okay, so this part, okay, this is completely new already. So if the first part bore you, hopefully this part will be more fresh. Okay, so besides all the apparatus that we use to contain and all right, we haven't covered apparatus that we can use to actually collect and dry gas. Okay, so in chemistry, you will encounter many reactions that actually produce gas as a product. So can you remember from set 2? What kind of reaction will produce gas? Fire. Fire produces gas for all gas. But it burns out. Okay, something burning. What's the gas? Oxygen from burning. Burn oxygen. Okay, burning. What's another name for? What's the name of the reaction when you have burning? In the presence of oxygen, combustion. Okay, combustion reaction. What's the gas produced? Carbon. Carbon is the gas. Okay, carbon dioxide and water. Okay, water vapor. Okay, that's the normal one. I think there can be others. Okay, so you have incomplete combustion. Okay, there's different kind of reaction basically. But that's one of them. What's another one you learn? Chemical changes chapter. Huh? Acid plus metal. What's the gas produced? Hydrogen. One more. Acid. Okay, acid plus. No. Okay, acid plus metal carbonate give you carbon dioxide gas. Okay, so these are a few reactions that already produce gas. If you were to conduct or carry out these experiments, right, how do you actually collect and measure the volume of the gas? Okay, why is there a need to measure volume? Because it comes down to calculation, right? As scientists, we always want to make sure that when we carry out experiment, we are trying to study something. It's not I conduct, then okay, then I did it. Okay, I want to determine something. That's why I carry out the experiment. Okay. So if I were to get a gas produced from my experiment, how do I collect and measure collect and dry first? Okay, measure, that's what I already mentioned. How to measure the volume of the gas. Okay, gas stream. So now we are only focused on collection and drying only, which means what I don't really care about the volume. Okay, I just want to collect. I want to dry the gas. Okay, so why is there a need to dry gas? Isn't gas already dry? Okay, if your gas mixed in the air, right, okay, or your gas is produced from a reaction that is in a liquid form, your gas will be wet one. It's not the wet that it's a different kind of wet, like just that the gas is very moist. There's presence of moisture in the gas. And for most gases, right, actually you cannot see them. They are mostly colorless, right? So air, right, all your gases in the air around us, right, everything colorless. So you must, if you know that the gas is produced from a reaction, right, that, okay, for example here, my gas is going through water. Confirm wet on, right? How can you go through water without being wet? Then there is a need for us to dry the gas. Okay? But before, okay, drying is the next portion. First, let's talk about collection. Okay, so if I were to produce a gas, of course I want to collect the gas, right? But it's not so straightforward. I mean, I can actually just put a gas stream. Okay, But I think depends on the context. Okay, sometimes we just want to store them. There's no need to measure. And actually the gas range itself, right, it's not very ideal for storage. Okay, it's more for measuring. Then I reuse it for another time. If I want to store long term, I will consider these methods. Okay, so take note for these methods of collecting gases, right? There are 3. So every time the question asks you, how do I collect this gas or that gas? You only need to consider 3 different types. Okay, so I'll run through the 3 first, then I break them down. First one is called water displacement. What does displacement mean? Displacement means what? Anyone? You must call name already. See the name. You need to practice all your. Oh, no, right now. One more. Right now. Right, take up the space. Okay? Okay, so basically I'm just occupying the space of a previous occupant, right? I'm taking over the space. So in this case, the displacement, water displacement literally means I displace the water. I'm kicking I think someone will learn, right? The displacement density one, also called displacement, right? So I'm just kicking away the water, then occupying the space. So in this case, what is happening? The gas is being bubbled through the water, then the gas will slowly move through the water and be stopped here. Okay, at the top portion. Okay, first one, water displacement. Second method for collecting gas is called downward delivery. Okay, so as the name suggests, you are literally sending the gas to be stopped downward. It's from up to down. That's why it's downward. Okay, take note of the apparatus used. They always use a gas jar. Okay, a gas jar. And then they have what you call the delivery tube, just to send the gas into the jar. Okay. Then last but not least, the third one. Okay, it's just the opposite of downward delivery. So it is upward delivery. Okay, so very easy to remember. Water displacement, upward delivery, downward delivery. Okay. And the upward and downward are completely opposite. It's completely opposite. It's just I take one, I turn it upside down. I get the other one. Okay, so now the question is, right, if I get a gas, right, I have some random gas, right, how do I know which one to choose or which one is suitable? Okay, you have 2 considerations. Okay, did they write here? Okay, they did that. Okay, the 2 considerations are here written at the heading of the table. First one is I need to consider the solubility of the gas in water, whether or not the gas is able to dissolve in water. So it's not just a yes or no question. I mean, the answer is not just yes or no. There's 3 situations you must consider for this. Okay, the first one is if the gas is very soluble in water. Okay, so what happens if my gas is very soluble in water? Will it stay in water or can it come out? You will just stay in the water, then can collect. Cannot, right? So if I have very soluble in water, forget it. Cannot work. Okay. Next consideration is insoluble. It does not even dissolve in water. Can collect or not? Can. Okay. Third case, slightly soluble, which means a bit only. So can or not? Okay. For our case, okay, for your syllabus, slightly soluble still can collect. Okay, because it's only slightly soluble, so it still can escape. It doesn't. Okay, so I don't know if you all know fish breathe oxygen, yes, right? But is it gaseous form? Okay, it's the dissolved oxygen. So how the oxygen from in our air actually dissolved inside the ocean, inside the river, becoming aqueous form, right? It's dissolved, and then because water is slightly soluble, that's why the fish can breathe it as well. Okay. So the oxygen, if let's say I have something slightly soluble being sent through the delivery tube, okay, it is able to still escape and be collected here. Okay, so take note, only for very soluble cannot work. The other two can. Okay, so take note of the phrasing. The phrasing is solubility of gas in water. You must say in water. Why is that important? Why must I mention water? Why cannot just say solubility of gas? What's wrong with that? If I just say, oh, the gas is soluble, it's insoluble. What's missing from that? Is that information enough? If I just tell you that, why not? Why not? Is solubility the same for every solute and every solvent? Okay, it changes, right? In set one, you all learn. What are the factors affecting solubility? There's three, right? What are the factors affecting solubility? Okay, one of them is if I increase, then it's more soluble. Something to do with temperature. Temperature, right? Temperature. If I increase temperature, solubility increase or decrease? Increase, right? You think about your Milo, right? Or your tea. When I want to make hot tea, right? Usually I use hot water. I don't use cold water. If I use hot water, right, then the tea doesn't dissolve as quickly. Okay? So solubility is affected by temperature. Okay? Other than that, there's two more factors. Okay, that one is rate of dissolving. Different. Okay, so this one is the one that the lowest, the set ones always get confused. Okay, type of solvent is one. So the type of solvent that you use will affect whether the solute or the substance can dissolve in it or not. Okay, so not every substance behaves the same in a every substance will behave differently in the same solvent. So if I use water, for example, carbon dioxide can dissolve in water, but maybe another gas cannot. Okay, so this is what we mean by type of solvent. Then one more. Last one. I have type of solvent, then what's the opposite one? Okay, type of solute. Okay, the type of solute will affect whether it dissolves in whether it's able to dissolve or not. Okay, so this relationship between solvent and solute, right, is very different across different substances. Okay, so in this case, where we must mention water because a gas can be insoluble in water but soluble in another solvent. For example, in ethanol, or it can be open or vice versa. Okay, so you must mention the solvent here. Solvent very important. Okay, we cannot assume that you know that it's always water. Okay, so this is the problem with when you come to set 3, right? Or you come to secondary school. You always tell me, ask you what's the boiling point? Then you will tell me 100, 100, 100. Okay, 100 is only for water. Okay, but there's every substance has their own boiling point, melting point, as well as solubility. Okay, all these are physical properties that are unique to each substance. So you cannot assume that they are always the same. Okay, so clear this so far, this one? Okay, so let's look at the solubility of gas in water factor. If my substance is insoluble, very soluble in water, I just ignore. I cannot use this method. Forget it. I will consider the other two. Okay. However, if it's soluble, slightly soluble or insoluble in water, my gas, I can use this method. That's it. So this method only works for two kinds of solubility of the gas in water, insoluble as well as slightly soluble. Everything very soluble, just ignore. Or if you don't have the data, you don't know anything about the solubility of the gas in water, don't use this method. Do not assume unless you know for sure or the question tells you. Okay? Okay, next, the next factor or next consideration is your density of gas. Okay, so what's the formula for density? I think I asked before, right? Okay, mass over volume, but okay, we are not so concerned about that. We just need to know okay, they didn't write. Can you add in for yourself? Compared to air. Okay, so why must we compare the density to air? Why is there a need to compare? Why air and not something else? You look at the next picture. Why must compare to air? Why cannot compare to like water? Where am I collecting the gas? I'm collecting the gas jar, right? Then what is around, what is present everywhere? Air. So because I'm now focusing on collecting it in the presence of air, I must compare the density to air. Okay, so please do try not to mix up the two. So some students always think solubility of gas in air, then density of gas in water. So they swap around. If you swap around, confirm wrong. Okay, so please remember one consideration is you always talk about solubility of gas in water, then density of gas compared to air. How can you remember this is you remember water displacement, I look at solubility in the water itself. Okay, then the other two, it has to relate to the density of the gas, then you compare to air. Okay. Okay. So so examples here for water displacement, right? Just take note. Okay, usually we use it for a few gases like oxygen, carbon dioxide, hydrogen. Okay, I think these two should be okay, right? You know, right? They can dissolve, and the oxygen doesn't fully dissolve, lah. If oxygen fully dissolve in is very soluble in water, then we are gonna lose all oxygen eventually. Okay. Then same thing for carbon dioxide. That's how you get the acid rain, right? Then hydrogen, just take note. Okay, so now we move on to the other two, downward delivery as well as upward. Okay, so now is where you need to consider the density compared to air. Okay, so why do we need to compare to air? Like I mentioned, because you are storing it in air. So for downward, right, the density must be greater. Why greater than air? Where do I want to keep the gas? At the bottom, right? So if I want to have it at the bottom, my density must be heavier, right? Larger than air, such that when you contain the gas, right, it will be something like that. This is air, this is the gas. Right, the gas is below air. If it's opposite, then my gas will just escape, right? Because I'm trying to store it now downward. If my gas is less dense than air, then you just escape. Okay, so you can use a lot of logical thinking to understand why is it done like that. Okay. So likewise, if I say for our downward delivery is exact opposite, okay, I must have a gas that is less dense than air, such that it can be captured at the top portion. Okay, if it's more dense, then it will just escape again. Okay. Any questions so far? Okay, now, how do we know it's denser or less dense than air? What do you think we have to do? Memorize, is it? Okay, no need memorize. Must calculate. Okay, so textbook have periodic table, right? Okay, can you look at your periodic table? Let's recap a bit of how to use the periodic table. Okay, your calculation here, right? You must calculate because you want to compare the density to air. Okay, so can you please write down somewhere, right? Density of air. Okay, can you just write the magic number 29? Density of air. So you're always going to compare to this magic number 29. Okay, so if it's heavier, if it's denser than air, it must be greater than 29. If it's less dense than air, it must be less than 29. Okay, so very must remember. I mean, you need to know this number. You need to know the reference point. Okay. Next, how do we calculate the density of any gas? Okay, we must look at the formula. If I write the formula, then I must memorize, right? So look at the formula of gas. So if I say formula of gas, you must write the correct formula. Okay, so for example, oxygen, what's the formula? It's not O. O2. Okay, so if you say O, okay, later on in the syllabus we'll learn why it's O2 lah, not O. Okay, so you must write the correct one. So O2. Okay, so how do you calculate the density? Very simple. For chemistry, we assume the volume is constant. Right, so formula of density, right, is mass over volume, right? Mass over volume. We assume volume, assume one. Okay, usually it's mass over volume lah. So if I use K, okay, I don't use SI. Okay, never mind, just assume 1 unit of volume. Okay, if I assume 1 unit of volume, then what does the equation be? Mass density equals what? If I assume denominator is 1, then what does the formula become? Density equals mass. So what can we compare? Just compare them. Okay, because the volume is the same, right? My air is here, my gas is also here. Volume is the same. Okay, so I assume same volume, therefore I can compare mass directly. Okay, so can you remember from periodic table how do we read the mass? Which number is it? The bigger one or the smaller one? You look at any element, you go and look at any periodic table, find one element that you want. Tell me is the mass the bigger or the smaller number? Bigger or smaller? Let me write it. Now what's on? Watch. Hey, hello, is it the bigger or the smaller one? If you are having trouble, there's a legend. That's not very table in your book. That's right, last page. Last page. You look at the legend and you tell me is the bigger number or the smaller number the mass. Okay, the bigger number is the mass. So how do we calculate the mass of oxygen? Formula is O2, right? O, what's the mass? 16. Then what do I do? 16 times 2, how much? 32. So oxygen can use this method. So I compare, right? Oxygen bigger or smaller than 29? Bigger. Bigger than 29 means what? I must use the method that allows me to capture the more dense gas, right, than air. Which method? Downward delivery. Okay, can see that? That's why, okay, they didn't write here, oxygen also can. Okay, let's use the example that they wrote there to make, so I can convince you. Okay, hydrogen chloride, formula is HCl. It's actually a hydrochloric acid but gaseous form. Can you try calculating the mass of HCl? Calculate the mass of it. Use your periodic table. Okay, you follow the formula exactly. If there's one hydrogen, you take mass of one hydrogen. Then chlorine, you find mass of chlorine plus together. Okay, if there's a subscript, right, then you follow accordingly. Okay, let's just practice. We try HCl and SO2 also. Okay, SO2 is sulfur dioxide. Okay, hydrogen chloride is HCl. Okay, then we try, we do all this practice now, okay? Can you all calculate for me? Give me the math. Hey, please try, please try. At least try one, even if you don't really feel like. Okay, I want to call name. I need to register. The front people, I think, I always see their name. Give you first page. Okay, don't need to think so much. The formula I already give you. I wrote everything there. You just follow the formula and calculate. Don't need to overthink. I think some of you are thinking of ions, right? Don't need more ions. Okay. Okay, we start first. Okay, I'm waiting for Zyler. Zyler, which one you choose? Okay, you need to familiarize yourself with where the elements are. You don't stare for 5 minutes, cannot find, then later time's up. Okay, Tyler, hey, Xiao. Okay, what? Give me the working. Okay, 1 plus 35.5 for HCl equals 36.5. Okay, thank you. Okay, so convince 36.5 is greater than 29 and use downward delivery. Okay, next one, SO2. SO2. Hey, this one simple computation and you all say or what? I'm not sure. Hey, can you all put the thing on your screen? I don't want to guess your name. Okay, 64. Working, please. Okay, 32 plus 16 times 2 for SO2 is 64. Okay, Cl2 is 35.5 times 2 equals 71. Okay? Okay, whatever the gas is, doesn't matter. As long as you have the formula, it confirms and calculate. It's just whether or not you key your calculator correctly or not, or you read correctly. Okay, so please open your eye quickly, look at the formula. Okay, don't misread the numbers. Can So I quickly go through for the less dense one, they only give one example, ammonia. What's the formula for ammonia? Anyone knows? NH? No, it's not NH4. NH3. I think you're thinking of NH4 plus. Okay, ammonia is NH3. What's the density or what's the mass? 14 plus 3. How much? 17. Less than 29? Yes. So can use upward delivery. That's it. Okay. So if you can do this fine, later on there's another portion we also will calculate one. So please you need to get very confident at calculating based on the formula alone. Okay. Later on, even worse, right? When you go for your end of year exam, right? No formula one. Everything you come out yourself. Okay. Okay, now we are done with this. Any questions? Okay, so what are the two factors I need to consider if I want to collect a gas? First one, solubility in water. Okay, so what kind of solubilities am I looking for if I want to collect between water displacement? Soluble only. What kind of soluble? Insoluble and slightly soluble. In very soluble cannot. Okay, very soluble cannot. Next one, next factor, second one. Density of air of what? In water. Okay, density of gas compared to air. Okay, please don't mix up water and air. I know blah blah blah. You mix up, game over already. Okay, density of gas compared to air, we compare to what number? 29. Then you go and calculate based on the formula of the gas. Okay. For now, we will probably provide you if we want you to calculate. Okay. Okay. Now we move on to the next. Yes. Okay. Next portion, we are going to talk about drying gases. So, like just now I mentioned, why do you need to dry a gas? Sometimes the gas produced from solution, then it will absorb moisture. I don't want the moisture in my gas, so I need to remove it. Okay. There's only 3 methods. Okay, this one is really memorized one. Okay, 3 methods only. Okay, first method is using concentrated sulfuric acid. Anyone can tell me formula? I think I asked before, right? Formula, sulfuric acid. There's something in front. H. No. H. Hey, you all learn this last year, right? Can't remember. H2 S SO4. H2S. Good. Okay, H2SO4 is sulfuric acid. I mean, okay, I'm not trying to test you the formula. I'm just asking you if you remember only. Okay. So first method, concentrated sulfuric acid. Okay, I go through the methods first. Second method, quicklime. Quicklime is the trade name or the common name. It's like you call sodium chloride salt, right? You call it an easy name to remember. Okay, quicklime is the I write here. It's called the trade name. Okay, then this one is the chemical name. different. So sometimes we can, it's like ammonia is a trick name. Ammonia, the name itself doesn't tell you anything about the formula. Okay, so same thing here. Quicklime is a word we use lah. If I say, oh, I need to buy some quicklime, but I'm actually referring to the chemical calcium oxide. Anyone can tell me formula? Formula. Okay, this one very easy one. This one just read off periodic table now. No, see, done. Okay. Of course, it's not everything so straightforward. Not everything oxide. Then I just write the formula like that. Okay, later on we'll talk about how to balance. You all never learn ions, right? Have you all learn ionic bonding? Have Why some say yes, some say no? Like that? A bit. Okay, later on there's one chapter on ionic bonding. Okay. Okay, so CaO is calcium oxide. This is the second method. Last method is fused calcium chloride. Anyone know the formula? Is it CaCl? I mean, if I read the name right, calcium chloride. Like that? Like that? So straightforward. Then like that, everything I just write the name lah. Okay, this one is wrong Okay, this one is KCl2. Okay, how those people who say yeah, then how? Why is it like that? Okay, calcium is 2+, chlorine is minus. Then you must balance out. So I need two chlorine ions to balance out one calcium ion. So the ratio is 1:2. Okay? Okay, don't worry so much about this for now. Okay, slowly we will get there. Okay, so 3 methods. First method is concentrated sulfuric acid. Second method is quicklime. Third method is fused calcium chloride. Must you write the word fused? Must you write the word concentrated? Yes, please. Okay, if you don't write, then there's no distinguishing them from the normal one, like the regular one. This one we are using specially as what we call drying agent. Okay, drying agent. So drying agent is just substance used to dry agent used to dry. I mean the name already say, right? Okay. So these three, if the question asks, what should I use to dry? Your answer can only be quicklime, fused calcium chloride, or concentrated sulfuric acid. Only 3 options. So far the answer, whatever we've covered so far, very easy. It's either downward delivery, upward delivery, and water displacement for it's either up or down. How you connect to the side? How do you ensure that the gas goes to one side? What do you learn? You all learn in lower side, right? Can you control the movement of the gas or not? Yes. How you control? How do you move from left to right? How does the gas move? What is the name of the phenomenon that the gas will travel? I spray perfume, then move from here to there. Diffusion. Diffusion after a while will still carry on. Eventually will come to a equal concentration. So I cannot enforce that, right? I can start maybe at the start 10. Over time cannot. Okay? So good point. Later we will learn diffusion also. Okay? Then maybe can kind of answer your question. Okay. Now the question, now the next portion is how do we choose which method to use? Okay, this part really memory one. Okay. So you think about this. Okay. If I want to use a certain method, you just need to think about which method will react with my gas. That's it. If it react, can dry or not? Cannot lah. So I must choose a method that doesn't react with my gas. So for example, sulfuric acid is what kind? I mean it's an acid, right? So I must use what kind of gas? Can I use acidic gas? No, use alkaline gas. But if I use alkaline gas, won't it react? Okay, so you think if I have an acid, then I cannot use alkaline gas. The alkaline gas will react with the acid. So what kind of gas can I use? Acidic gas okay, which you haven't really learned yet, but just keep KIG. Okay, so for your case now, just memorize. Okay, so most gases can use this because actually, okay, anyone knows what? Name me one alkaline gas. I think you learned one, right? Go one of your tests for gases. Your gas will turn the red, then red reverse paper blue. One of it. Which one? Nitrogen? No, not hydrogen. It's on the board. On the board. Ammonia. Ammonia is NH3. Ammonia NH3. It does. Ammonia is an alkaline gas. Alkaline. Okay. So actually, that's why they say most gases it works, because for so far only ammonia you learn in your syllabus. Ammonia is an alkaline gas, so it doesn't work for ammonia, but it works for almost everything else. Okay. Then here example ammonia. They really write. Okay. But the idea is because ammonia as an alkaline gas, it will react with the acid. If I react already, I cannot dry it. It's just gone. It becomes a salt. Right? I form a salt and water. Gone. Okay. 10 so far. Next one. Quicklime. Okay. Idea is exactly the same. I want to use a gas that does not react with quicklime. Okay. So quicklime is actually okay. It's not really. Okay. Quicklime is a base. A base. So same thing, right? As a base, it will react with what? Acid lah. So I cannot use acidic gas. Cannot use carbon dioxide. Okay. So you just remember, carbon dioxide is an acidic gas. Okay, why is that acidic gas? Your carbonated drinks, your Coke, your Pepsi, right? When you open, got sound, right? Because it's an acidic gas inside. Okay, so it's carbon dioxide inside. It's not die. Okay, acidic doesn't mean you'll die. Okay, you all learn right in sec 2. How does the acid taste? Sour lah. So everything you eat sour is all acid. What? You will die when you die already. Okay, you drink lemon juice, you die, is it? Yeah. Okay, you show me. Okay, you drink here, then you die. With lemon juice. Or you okay? Okay, yes, if it's too acidic, maybe like pH1 or pH0, then of course you'll get in trouble. Okay, but remember your pH scale. That one should die one. Okay, so your pH scale is 0 to 14, right? Then acid is what? pH. Okay, acid is 0 to 0 to what? 6.1. Okay, just do less than 7 lah. Okay, then base. Okay, I'll say alkaline. More than 7. Okay, so even if it's 6.9, 6.8, 6.9 is still acidic, but it's just not very acidic. So that's usually the acid that you consume. Even vinegar is an acid. Okay, your citric acid from your fruits is also acid. Okay. Okay, so just take note of this. What another thing to note for this method is that it will absorb. This will absorb carbon dioxide from the air. So after a while, you cannot use it anymore because it will absorb the carbon dioxide, which will affect the quicklime itself. So you can only use it fresh. That means if I leave it after some time, right, this method won't be as effective. So just take note of this. Okay, then like I mentioned just now, it cannot be used to dry gases which react with carbon dioxide, react with calcium oxide. Okay, so if you have a gas that is alkaline, can use so this will work for ammonia. Okay, see, it's actually opposite, almost opposite of the previous one. Okay, because one is a base, one is an acid. Okay, so no matter what gas I have, there's always a method that can use to dry one. Okay, so don't need to worry so much. Okay, last one. Calcium chloride. Must write the word fuse. Okay, so take note. Okay, you might want to pay attention to the drawing. Sometimes they do test the drawing. The drawing of this diagram. Okay, so just take note, it's always the moist gas in. The gas is wet. Gas go in, come out, become dry. That's it. Okay, so whether it's concentrated sulfuric acid or whether it is my quicklime, same thing. I send in moist gas. Okay, the drying agent will absorb all the moisture away. Then you have dry gas that leaves. Okay. Okay, last one, your fused calcium chloride. Okay, notice that they are all in the form of pellets. Okay, so they are just, pellets, small ones. So they are just lining up the tube with pellets. Then as the gas pass through them, right, the pellets will absorb the moisture. You will capture the water. Okay? Yeah, something like that. Yeah, so it will just, in a sense, the water will be attracted to the drying agent. So it absorbs. I mean, for lack of better word, just attract. Okay? Okay, example, what can you use to fuse calcium chloride to dry? Okay, a lot of examples. So same thing. You cannot use it to dry gas which react with fuse with calcium chloride. So the only example you need to take note of is ammonia cannot be used for this. Ammonia reacts with calcium chloride. So if you think about it, ammonia only got one method, right? Which one? Quicklime. Fused calcium chloride cannot use for ammonia, as well as concentrated sulfuric acid also cannot use for ammonia. So you only got one method left. Okay, so ammonia, you see the word ammonia, quicklime, no choice. Okay, you say why? Okay, so same thing for fused calcium chloride, it also absorb moisture from air. So you must be freshly, it must be freshly heated. Okay, did you say heat just now? Oh, freshly heated. Okay, so same thing the fused calcium chloride as well as your quicklime, right? They must be prepared fresh. If not, they will absorb a lot of moisture. Then the efficiency will drop. Okay? Then clear. I'm done already. I mean, I'm done with this part. Any question? Okay, so just to summarize what we covered today, actually it's quite a bit. So we covered 3 types of gas collection method. Okay, what are the 3? You just name for me. Come, let's just summarize. Okay, gas collection. Okay, water displacement. Then outward delivery. To write on my. Yeah, I tell you what, because I'm recording, I write here. Okay, just nice. What can I fill in? Where's the L? Okay. Then downward delivery. Okay. Okay, what are the considerations for gas collection? 2 considerations. 2 factors to consider when you want to choose gas collection method. Density of gas compared to air. What's the number? 29. Okay, notice I never give you units because it's not so important because everything same unit. So there's no need to compare the unit. Okay, you can just compare number. Second one, solubility of gas in water. Okay. Okay, then density of gas, if it's less dense, which method? Okay, less dense is upward. Okay, less dense. I don't know if this makes sense. Okay, less dense upward. Then more dense downward. I need to go on wrong. Does it make sense, right? Okay, more dense. Okay. Do I need to consider about solubility of the gas in water if I want to use, if I already know the density? Don't need right? If I already know this method work, why do I need to consider unless the question say how many methods can be used? Then you will consider, I will look at solubility as well. Okay, good question. How do I tell which is better? Okay, for this portion, right, we won't ask you which is better because there is no better. We just ask you which is suitable or which can be used. Okay, so as long as the method that you choose, right, is scientifically plausible, it makes sense, then okay, we'll accept. Okay, good question. Because when we talk about choice of apparatus, usually we are focused on the best one. But this one don't have best. I mean, it works already. Why do I need a better one? I drive faster, maybe. Okay. So don't worry. If you need to compare between, I will tell you. So for one, apparatus must compare between them. Which one is the best at carrying out for a certain function that I want to carry out. Okay. Okay, less dense. Okay, what about solubility of gas in water? What kind of solubilities do we consider for water displacement? Okay, insoluble and slightly soluble. Great, wow, you all catch everything. So can go for TP already, right? Set 1 got TP, oh yeah, low set have, right? Okay, yes, okay, so I need to talk to you all about the TP. Okay, we already for chemistry this year, we will have the WAs, right? I need to emphasize first, right? We don't have a lot of paper plans there. Which is, actually, I don't know you're happy or not, but it's actually quite bad because you can check with your seniors. A lot of them for last year, they did very well for WA1, that means they got like 100. Come to EOY, 2 single digits. Because they don't know, they thought, oh, I'm gonna get 2 marks because I got 2 marks for my project. But then keep in mind, your assessment may not translate to your result because the WA assessments may not directly translate because the WA is a lot about skills. But when it comes to exam, right, whether you have the exam skill is really determined by how much you have taught from the lessons in class. So mainly your PP performance. So I hope that you can take every PP very seriously. I know it's not graded, but that's not the point. It's not, oh, it's graded, then I study, right? Then not graded, I don't study. Okay, so it just for you to take note of, because I have students coming, wow, I did so well for WA1 and 2. Then suddenly come EOY, I failed. Okay, because the assessment mode is slightly different. So just keep that in mind. Okay, slightly soluble. Then last but not least, okay, just nice we are ending. What are the 3 methods for drying gas? What are the 3 methods for drying gas? Condense, no. Drying gases. Quicklime. What is the chemical name for quicklime? CaO. Name. Okay, calcium oxide. Quicklime, aka calcium oxide. Second one. Okay, this one is calcium oxide. Second one. Fused calcium chloride. Last one. Concentrated what? Concentrated sulfuric acid. Okay. For the drying agents, please go back and revise which one cannot be used for what purpose. Okay. In general, for your drying agents, right, you cannot use them if they react with the gas you are trying to dry. That's it. Okay. But you should know a few examples of what cannot be used. Okay. So in general, quicklime, just know that it's a base. And sulfuric acid, like the name, is an acid. So you cannot use acidic gas for this. You cannot use alkaline gas for this. Okay. So this one a bit more memorizing part. Okay. Any more questions? Okay. So we are done with the first part. For the next lesson, okay, we will talk about separation of mixture. So it's basically your set 1, your physical, your separation techniques. So you will see this, if I scroll down, everything learned before, right? Filtration, evaporation of dryness, simple distillation, all these learned before already. But we have a lot of new ones. See, now got 11. Right, you got 4, 4, 3. Now got 11. Last year, set 1, you only learned 5. So we are going to add another 6. Okay? And not only that, we will talk about them in more greater detail. Okay, set 1, it was more like exposure, let you try out only. Now we'll do a lot of calculation. Okay. Okay, if no questions, class 10.